The moon is brown, not gray, not white. Brown. That is what the Artemis II astronauts said out loud on a live NASA broadcast. And for approximately 4 seconds, nobody in mission control said anything back. 4 seconds does not sound like a long time. Until you understand what was sitting behind that silence. These were not tourists pressed against a porthole for the first time. These were NASA-selected mission specialists with thousands of hours of training, geology briefings, high-resolution lunar imagery burned into their memories across years of preparation. And when they finally saw the actual moon with their own eyes, from closer than any human being has been in over 50 years, their reaction was visible surprise, on live television. That reaction is the story, not the mission, not the flyby trajectory, not the press conference talking points about Artemis III and what comes next. The reaction. Because what it tells us is that every photograph, every telescope image, every rover frame, every orbital map we have ever studied has been showing us something that is not quite real. Not intentionally, not as a conspiracy, but mathematically, physically, optically, lying. The real moon and the moon we thought we knew are not the same object, and scientists are only now beginning to calculate what the gap actually means for the astronauts. NASA is planning to land there in less than 24 months. Artemis II launched in 2025. 4 astronauts. Commander Reed Wiseman, pilot Victor Glover, mission specialist Christina Koch, and Canadian Space Agency astronaut Jeremy Hansen completed a free return trajectory around the moon. No landing, no surface contact. Just the closest crewed pass since Apollo 17 departed the lunar surface in December 1972. Over half a century of distance, closed in a single mission. The official purpose was systems validation. NASA needed to confirm that the Orion capsule and the Space Launch System could execute a crewed lunar transit before committing to a landing. That is the press release version, the one with the triumphant orchestral music and the slow-motion launch footage. But inside the capsule, during the approach, something happened that did not make the highlight reel. The crew began describing what they were actually seeing, and it was not what they had prepared for. The detail that stopped scientists mid-sentence was color. The crew described the lunar surface as distinctly brown, not as a subtle shift or a minor variation in tone, but as a striking, unmistakable difference from every image in their training library. This registered on the faces of people who are professionally selected, in part, for their ability not to be surprised. And they were surprised. The moon's surface is covered in regolith, a fine, compacted powder of pulverized rock ground down by billions of years of micrometeorite impacts. Embedded in that regolith are iron-bearing minerals, primarily pyroxene and olivine. Under the right lighting conditions, particularly at oblique angles, both minerals shift visually toward brownish tones. Geologists have known this since Apollo returned the first soil samples in 1969. It is documented, it is understood, it is in the textbooks. So here's the question that nobody at the press briefing wanted to ask out loud. If the brownish coloration is fully explained by known mineral chemistry, chemistry that trained astronauts had studied for years, why did the color come as a surprise? Why did faces change? The answer to that question does not close a gap. It opens one, a gap between what instruments measure and what a human visual system actually perceives when it is sitting 239,000 miles from Earth, looking at sunlight bouncing off a surface with no atmosphere to scatter or soften it. That gap is now NASA's most urgent pre-landing research problem. Artemis III is targeting the lunar South Pole, a region that has never been visited, never been walked, and never been seen by human eyes at surface level. Sunlight at the South Pole arrives at extreme low angles, between 1.5 and 3 degrees above the horizon. That is not overhead illumination, that is almost horizontal light, grazing across every ridge and crater rim, casting shadows that stretch for kilometers and saturating every mineral surface with side-lit color that overhead photography has never captured. What the Artemis II crew confirmed, without intending to, is that the human visual system and every camera system ever sent to the moon are not equivalent observers. They do not see the same thing. And nobody had built a model for what that difference means for astronauts who need to navigate, collect samples, identify hazards, and find their way back to a lander on a surface they are encountering, visually, for the very first time. This is where the story stops being about color and starts being about whether people come home. Lunar surface operations for Artemis III are built almost entirely on visual contrast. The astronauts need to read terrain in real time, distinguishing stable ground from loose regolith, identifying rock types for targeted sample collection, recognizing the visual landmarks that lead back to the lander. Every one of those tasks depends on seeing the surface accurately. In every training simulation, every EVA rehearsal, every navigation protocol was calibrated against photographic data captured by instruments that do not see what a human eye sees. The Lunar Reconnaissance Orbiter is NASA's most detailed current mapping asset. It has produced the highest resolution images of the lunar surface ever created, But it captures data in specific wavelength bands, then processes and displays those images in a color space optimized for scientific interpretation. That is not what Victor Glover's eyes were doing when he looked out the window of the Orion capsule. His visual cortex was doing something fundamentally different, integrating wavelength, brightness, contrast, and spatial texture in a way that 50 years of camera technology has never replicated and never needed to, until now. NASA has spent approximately $93 billion on the Artemis program as of 2025. The dominant risk category in internal surface operations safety assessments is astronaut mobility and navigation. Falls, disorientation, terrain misidentification during EVA. These are not hypothetical risks. They are statistically modeled outcomes built from decades of planetary surface data. And the visual data feeding those models was generated by instruments that the Artemis II crew just confirmed do not match human perception. That is not a footnote. That is a structural problem at the foundation of the entire surface operations plan. Think about what that means in operational terms. An astronaut steps out of the lander at the lunar South Pole. They have practiced this moment hundreds of times in simulation. They know the layout of the landing zone from orbital photographs. They know which direction to walk, which rocks to prioritize, which terrain features mark the path back. And then they look up, and the surface looks different. Not completely unrecognizable, but shifted. The shadows are longer and darker than the renders showed. The ground color is warmer. The contrast between light and shadow is more extreme than any training image conveyed. Every visual reference they built their confidence on is slightly wrong. And they have to make decisions anyway, in real time, in a suit that costs more than a commercial aircraft, on a surface that will not wait for them to recalibrate. Within days of the Artemis II flyby, geologists at the Lunar and Planetary Institute and at NASA's Johnson Space Center Curation Facility began pulling Apollo-era sample data. The goal was precise: determine whether the brownish tones the crew described were consistent with the known mineralogy of South Pole-adjacent geology, or whether something about the lighting geometry at that specific orbital distance and sun angle was producing a perceptual effect that no sensor had ever been calibrated to record. The Apollo program returned 842 pounds of lunar material across 6 landings. That collection has been stored in nitrogen-purged vaults, cataloged to the gram, and analyzed by researchers for over 5 decades. It is one of the most studied collections of extraterrestrial material in existence. But almost none of that study has been conducted in the context of what the samples look like to a human eye under conditions that simulate direct, low-angle sunlight at the lunar surface. Controlled laboratory lighting is overhead, diffuse, and constant. The lunar environment is none of those things. The two visual contexts are not comparable. NASA is now reportedly running illumination experiments, placing Apollo sample trays under simulated low-angle solar light sources to test whether the brownish tones the Artemis II crew described are reproducible in a controlled setting. If those experiments confirm the effect, and the explanation is mineralogical, and the primary response is recalibrating training visuals and navigation simulations before Artemis III. That is a solvable problem. Difficult, time-constrained, but solvable. If the experiments do not reproduce the effect, the implication is significantly more unsettling. It would mean that what the crew observed was a product of the optical environment of cislunar space itself, and no instrument currently in orbit or on the surface is designed to measure it, because no instrument was ever built with a human retina as the reference point. Here is the number that should have been the lead on every space news platform the morning after the Artemis II flyby. This is not the first time astronauts have said the moon looks wrong. It is the 6th. Apollo 8, December 1968. Frank Borman, Jim Lovell, and Bill Anders became the first human beings to see the moon from close proximity in real time, and their verbal descriptions during the mission were emphatic and specific. The surface looked nothing like the photographs. The shadows were absolute black, a depth of darkness that no image had conveyed. The contrast between sunlit terrain and shadow was so sharp it registered as almost theatrical. Apollo 11. Neil Armstrong's post-mission technical debrief contains explicit language about the visual surprise of the surface color and how it diverged from training imagery. Buzz Aldrin described the ground beneath his boots during the EVA in terms that do not match the gray palette of any photograph taken on the same day. Apollo 12, 14, 15, 16, 17. The pattern holds across every mission that put humans on the surface. Astronauts consistently described a visual reality that did not match the photographic record. Those descriptions exist in the transcripts. They have been publicly available for decades, and they were set aside, not suppressed, not classified, just noted and filed and left unresolved because after Apollo 17 lifted off in December 1972, there was no program that needed to act on them, no follow-on crewed mission, no one going back. The data gap was real but inconvenient, and inconvenient data without a mission to solve it tends to sit in archive boxes until something forces it back into the light. Artemis II just forced it back into the light. We have more images of the moon than of any other object in the solar system outside of Earth. We have terabytes of spectral data, gravity maps, thermal scans, and radar cross-sections. We have mapped craters down to 1 meter in diameter across the entire near side. And we apparently do not have an accurate representation of what a human being standing on the surface will actually see. 6 landings, 12 moonwalkers, decades of recorded visual discrepancies, 0 systematic research program to close the perceptual gap. That is an extraordinary statement to make in 2026. The projected cost of Artemis III is estimated between $4 and $6 billion for a single flight. The space launch system that carries it to orbit costs approximately $2.2 billion per launch. Every EVA traverse, every sample collection sequence, every navigation decision on the surface was designed and rehearsed using visual models that were never validated by direct human observation. 4 astronauts on a flyby just raised their hand and said the models might be wrong. The launch window has not moved. When a program of that scale rests on a visual assumption, the assumption that photographic data accurately represents what a human eye will see, and then the first human eyes to verify that assumption in 52 years report a meaningful discrepancy, there is only one correct response. You stop. You run the numbers again. You do not continue on the same schedule and hope the discrepancy is small enough not to matter. Not when the people relying on those numbers are going to be standing on the surface in pressurized suits, making navigation decisions in real time, in a visual environment that may look materially different from every simulation they trained against. NASA has approximately 12 to 18 months before the Artemis III launch window. That is the full available timeline to study the Artemis II crew's observations, update the surface training visuals, recalibrate the EVA planning tools, and validate the results against the best available simulation of South Pole lighting conditions. 12 to 18 months for a problem that has existed in the mission record since 1968. The math on that timeline is not comfortable. Step back for a moment and consider what this means in context. We are living in an era in which artificial intelligence generates photorealistic images of places that have never existed, in which commercial satellites can resolve individual faces from low Earth orbit, in which the James Webb Space Telescope identifies the molecular signatures of water vapor and carbon dioxide in the atmospheres of planets orbiting stars 1,200 light-years away. The most advanced imaging capability in human history exists right now, operating right now, producing data right now, and the single closest astronomical object to Earth, the object that humans physically visited 6 times, that has been photographed continuously for over a century, that is visible without a telescope from every backyard on every continent every single night, has never been accurately documented in the one dimension that matters most for the people we are about to land there. What does it look like to a human eye? That is not a gap in our technology. That is a gap in the questions we thought to ask. The cameras on every lunar mission were designed to capture scientific data, mineralogy, topology, albedo, navigation references. Nobody designed a camera to answer the question of what the surface looks like to a person, because the assumption was that a camera and a person were equivalent observers, that the image and the experience were the same thing. The Artemis II crew just walked up to that assumption and publicly broke it, on broadcast television, in front of a global audience, and the assumption has not been repaired yet. The implications do not stop at the moon. When we send humans to Mars, which every major space agency with a crewed program is actively planning, the same gap will be waiting. The same assumption will be embedded in every training simulation, every surface navigation model, every EVA protocol. Except on Mars, the crew will not be on a flyby. They will be on the surface, between 8 and 24 minutes of communication delay, away from mission support, in an environment no human has ever seen, with no option to abort. When the surface looks different from the simulations, there is no one to call in real time. You adapt or you don't. The moon looked wrong. That is the sentence. Not catastrophically wrong, not dangerously wrong, not in a way that ended the mission or triggered an emergency abort, but wrong enough that 4 of the most thoroughly vetted and rigorously trained observers in the history of space exploration reacted with visible, involuntary surprise. Wrong enough that geologists in 2 facilities immediately began pulling half-century-old sample data to understand why. Wrong enough that the foundational visual assumption of a $93 billion surface operation plan is currently under active review with fewer than 18 months before the launch window. There's no going back from that data point. The Artemis II crew flew around the moon and confirmed in real time what the Apollo transcripts had been quietly recording since 1968, the object that has been photographed more than any other body in the solar system, the object that is visible to the naked eye from every continent every night without any equipment whatsoever, the object that 12 human beings have walked on and returned from alive. That object is not the same thing as the images of it. The gap between the picture and the reality is real, it is measurable, and it is now officially on record. For the astronauts who will land there next, that gap is not a philosophical curiosity. It is the most consequential unresolved variable in their mission plan. The math does not forgive omissions. 6 landings, 12 moonwalkers, 55 years of documented visual discrepancies, 0 systematic research program to resolve them. And now, finally, a reason that cannot be deferred. We are going back. The window is open. The clock is running. And we still do not fully know what we will see when we get there.